because I've done facial yoga. Okay. So last time we were talking about center of mass. And we found out what it would be for a discrete distribution of mass. So a discrete distribution of mass means that I have these smallish particles located at different x and y coordinates. And so each mass, mi, is at some xi and yi. And of course, these are my x and y coordinates. And then we had expressions for how we were going to write the x center of mass and the y center of mass. And remember, this is how we started talking about summation symbols, because it was the summation from I equals 1 to n of the mass of each object times its x coordinate divided by the total mass. And for y, it was again the summation, so I'm adding up the contributions from all of the particles of mi yi over m. And again, m is that total mass that I can also write as a summation. And hopefully after what we did yesterday and what we did in calc this morning, summations are not as esoteric, terrifying, whatever. Okay? Esoterrifying, I like esoterrifying. Okay? And of course, I could write a similar expression for z, but I'm only working in 2 dimensions, as we will most likely be doing. Okay? We also talked about combining this all into a vector, so I could have r center of mass, which would have I, j, and k terms that were the center of masses in the x, y, and z direction, respectively. But the problem that we were starting to talk about at the end of class was that sometimes there are too many particles to add up. If I wanted to find the center of mass of this cube of paper, and I was going to use my discrete distribution of mass, I would have to find the x and the y coordinates and the mass of every tiny little particle that makes up every piece of paper in here. And that would be really hard. So in the case of the paper, in the case of you, in the case of my water bottle, or all kinds of things, we don't have a discrete distribution anymore. What we have is a continuous. Distribution of mass or matter or material or whatever you want to call it. And we must be a tiny little bit behind in calculus. We are. If we hadn't done that stupid journal problem that doesn't matter, we would be exactly where we need to be right now, but we are not. Okay? So, I'm going to spoil my own thunder for Tuesday. All right? So, we were talking about summations and adding things up. But in the discrete case, my summation really went from I equals 1 to n, where n was some value. N was the number of particles that I was adding up. It could be 4, it could be 100, it could have been 1,000, but it was some finite number. When I'm taking a continuous distribution, what I'm really doing is adding up the contribution from an infinite number of particles. because I can always break something down. I can always take my molecule and turn it into atoms. I can turn my atom into neutrons and protons and electrons. I can turn my protons and electrons into quarks. Okay? So I can always keep breaking things down. And scientists probably think that quarks break down into something else. We just don't have enough energy yet to smash it. So what I'm really doing is summing over an infinite number of things. And in the process of summing over an infinite number of things, in the process of taking my sphere and breaking it into an infinite number of pieces, is that each of those pieces becomes infinitely small. Right? Okay, it's like dividing by infinity, which you can't really do. But if I'm going to keep breaking it into smaller and smaller pieces, eventually I'm going to have an infinite number of them, and they're all going to be infinitely small, infinitesimally small, just because I like to say that word. When you add up a bunch of infinitesimally small things, as we will discover in calculus on Tuesday, and Elisa learned last year, that summation becomes an integral. And we'll build up to it more when we do it in calc. So let's talk about how this really works if we consider a sphere with, and this is important, a uniform distribution of mass. Or a uniform density. So here's going to be my sphere. And my sphere is made up of infinitesimally small pieces that all contribute to what the center of mass is. So I'm going to have some tiny little point here that's going to have some mass dn. It's a differential, as we'll find. And it's going to be located at some position xi, yi, zi. Actually, I take that back. It's going to be located at xyz. Okay. And so remember back here when we were talking about the discrete distribution of mass, what I did was I added up the mass of every particle times its position, right? And then I divided it by the total mass. So when I'm talking about the uniform distribution, and I'm talking about that X center of mass, I'm still going to divide it by the total mass of my sphere. And I'm still going to take each particle that has a mass dm and multiply it by its position. But because I'm adding up an infinite number of them, which are infinitesimally small, instead of summing, I take the integral. And as you might suspect, I can write a similar expression for x, y, and z. Now, Now, we've talked about in this class, and we've talked about in AP Calculus, that one way of thinking about an integral is that we're taking the area under the curve. But we've started to hint at in calculus, and we've done it a little bit here too, that taking an integral can also be looked at as taking the antiderivative. Remember, we've talked about inverse operators, sine and inverse sine, squaring something and taking its square root. Inverse operators undo each other and give us our answer back. Okay? Derivative and integral are effectively inverse operators. So they give me something back. So taking the integral of something is the same thing as taking the antiderivative, undoing the derivative and getting my initial value back. Okay? So I'm going to vaguely explain why this is a little complicated. Elisa may be the only one who really gets it at this point, but again, stepping stones, okay? One of the things that we do when we take an integral, especially of something finite, is we put limits on our integral. And remember, we did that when we found the work done by an object in this class. When we found the area under the curve, we were finding it between two specific x values. Okay, so we put limits on our curve. And those limits related to our variable of integration, which was indicated by the d something. So for these three integrals, I'm integrating over mass. Elisa, that should make your skin crawl. What do you mean integrating over mass? I'm not integrating over mass. Okay. And what would the limits be? It's not like I'm applying it from like 0 to x equals 4 or something. It's the mass. Okay, so it's not a straightforward thing to integrate over, but we can use the fact that this is a uniform distribution and has a uniform density to kind of change these equations a little bit. Remember also when we were doing integrals, if something was a constant, I could move it out of the integral. Okay, like if it was a 2 or a half, I could kind of bring it out before I evaluated it. But is x going to be a constant? No, okay, because every particle on this sphere has a different x. Not entirely true, but you get my drift. Okay, so I have a variable here, and I'm integrating over another variable that isn't that one. That's like taking the integral of giraffe dx. The heck? Okay, you don't know how to do that. So I want to show you one way to make this simpler because, again, it's a life skill. Remember how we did that thing with the pendulum where the pendulum was down here and then the pendulum came up and we did the thing with the triangles and how this was L and this distance was L and you could figure some things out when we were doing energy? Life lesson apparently not learned. That was a technique that you'll be using over and over again. And in fact, it came up on something and I said, hey, remember I told you you had to remember how to do this in class? Yeah, okay. This too is a technique that you may find yourself in a position to use. Okay, so if I think about mass density and I have my rho, how do you express density? It's a mass density though. Mass over volume, okay? Density is always going to be per volume. So I might say that this was equal to the total mass divided by the total volume. Yes, so this is mass density. Okay. But if my density is uniform, that means that no matter what amount, what volume I take, the mass is still going to be proportional and I'm still going to get rho. So let's say I took half of the volume? Because it's a uniform mass, a uniform mass distribution, how much of the mass should I get if I take my sphere and cut it in half? Half. I should get half of the mass. Okay? And those halves cancel, and I get the same rho value that I had before. Infinitesimally. If I take an now you got me messed up. If I take an infinitesimally small mass, which is my dm, it's going to fit into an infinitesimally small volume, which would be dv. Okay? Whether I take a half of it or a quarter or a third or 10%, because it's a uniform mass distribution, I'm going to get the same amount. I'm going to get that same ratio. Okay? Think of it as vanilla ice cream. You have a tub of vanilla ice cream. No matter how many scoops I take out, right, because a scoop's like a semicircle, let's say, or a half of a sphere, okay, I'm going to, approximately, if you have an old-fashioned scoop, okay, I'm going to have that same relationship between mass and density. If I don't have vanilla ice cream, if I have, what? I was going for a non-uniform ice cream. Cookie dough would be good because those are pretty big chunks. Okay, the mass distribution in cookie dough is not uniform. That explains so much in my life and is a really good tip. So, but you could imagine, if you imagine a half gallon of cookie dough ice cream, that I could take a scoop of that ice cream that might only have one piece of cookie dough in it. Or if, as Zoe says, I'm at the bottom, I might have a scoop that is almost all cookie dough. I was trying to go for something more that had like veins. Like moose tracks. Okay, you know, something where, you know, like there's like, you know, did you ever work a vein in the ice cream? A vein like ore, like when you're mining and you've got like, I can't think of what it is. Oh, okay. Yeah. Yeah, you know, so you could see how you could make a scoop and it wouldn't be a uniform distribution anymore. But if I have a uniform mass density, then no matter how much of it I scoop, that relationship between mass and volume is going to be the same. Which means I can take this part and this part, okay, and these are constants, and I can solve it for dm. I am. It is, but I was recording my whole desktop, so I think it goes away. And I did that this morning because I thought I was going to be flipping between screens and calc, and then I didn't. Everybody is here, but I do still record just in case anybody wants to go back and look. So I think we are. You can do that if you wish. So let's just look for a minute at what our x center of mass equation was. So it was the integral of x dm over capital M and if I substitute in for dm, then that gives me x m over v dv all over m. It's, as we'll talk about in calc next week, it's more about being, it's a bookend, it's a indicator. It indicates what the variable of integration is. Because someday you will do an integral that looks like this. You'll do a double integral or a triple integral. And then you need to know that this part goes with this and this part goes with this. Oh, it's fun. You'll be fine. Spherical Bessel functions, that's the way to go. Okay. I substituted in for dm. So I solve for dm up here. Okay, with me? Yes. Okay. So for starters, I can cancel my m's. Not that it really matters, but I can. And then this 1 over v can come out because it's a constant. It's the volume of the whole sphere. And this leaves me with x dv. Yes. But, and when we were doing some of our related rate problems in Chapter 5 of AP Calc, okay, you would take a function for volume perhaps, and you would take the derivative with respect to height, or you would take the derivative with respect to radius. So what you would hope is that you could see how the volume of a sphere, which is 4/3 pi r cubed, that this r would somehow be a function of x and y and z, which you would know it would be, right? So you could somehow, from this volume expression, find a way to work your way to what x is, or work your way to a dx, okay, by taking the derivative of this cleverly, okay? So we're not going to actually do that. My point is more that someday you may have to. And if you take the second half of this class someday, when you have a lot more calculus under your belt, you'll end up taking these kinds of integrals and being comfortable with it. I promise. Okay? So, all of that being said, if I have a sphere of uniform mass distribution, where's the center of mass of the sphere? You got it. Okay, so it's in the middle. If I have a cube of uniform mass distribution, where's the center of mass of the cube? In the middle. Okay, so there will be a lot of situations in which you can use symmetry and geometry to help you figure out where the center of mass is. There's a couple of challenging problems that this involves, but nobody's really trying to trick you. Okay? And what you can also find is that, let's say what I have, it's not how I want to draw that. Well, here. If I have a rod with a ball on the end, okay, I could find the center of mass of the ball and the center of mass of a little bit, except that I believe on the homework question the rod was massless, but if it wasn't, okay, that was the ball. Okay, but what you could do is, you know, hey, I could let x be equal to 0 here, and I could have some coordinate for the x center of mass of the rod and another coordinate for the x center of mass of the ball. And if they're uniform, what I can do is turn this into a problem where I have something right here that has the same mass as the rod and something right here that has the same mass as the ball. And I can turn these two uniform objects into discrete objects and find the center of mass that way. Okay, so there are a lot of tricks that we will find and we will use. Okay, so you're probably not going to have to take many integrals. There'll be a couple, but not a lot. Okay, we good? We got it? Okay, then I think, we've got time to do a couple examples, which would make me happy if we got through the examples today. All right, so this is whatever the next sample problem is. There we go. So we're going to assume, although it's not true, that the moon and the Earth have uniform distributions of mass. They do not. They're not even like concentric things because of the whole gravity sink over the Indian Ocean. But if we do that, then we could assume that we could take the Earth and imagine that all of its mass is concentrated at its center of mass. So that instead of having this big Earth, I've just got all this mass right here in this point mass. Okay? And because the Earth and the Moon are, for the purposes of this class, far enough apart that they appear to be point masses. That's really not true, or we wouldn't have tides, but trying to make things simple. Okay, so if we let this be the Earth, some distance away, we're going to have the Moon. And again, we're going to do the same thing. We're going to assume it's a uniform mass distribution, which means that I can pretend that all of the mass of the Moon is concentrated at the center of the Moon. And the problem asks us to find this center of mass as measured from the center of the Earth. So that's where I'm going to let x be equal to 0. So then the question is, what's x moon? Google, or it's in the back of your textbook if you have your textbook. Or the front, it's somewhere in your textbook. Yeah, but that's usually how it's measured. We'll take 384,400. Because really, seriously, that 2 kilometers, I suppose we probably know it pretty good because we sent people there, but still. Okay. So what else do you need to know to find the center of mass? The masses of those things. So we need the mass of the Earth and the mass of the Moon. I know what they are relatively, but I don't know what either is off the top of my head. What's the Moon? I don't want garbage units. I want SI units. So we're going to have to convert that kilometer thing. I always think of it as 5.98 times 10 to the 24, so that's what we're doing. There's roughly like a 5-to-1 ratio. Yep, 10 to the 24th. Why we can't just call that 6, I don't know, but apparently it makes a difference. Okay. So we have all our numbers. And the x center of mass is going to be adding up each mass times its x coordinate. So I'm going to have the mass of the Earth times the position of the Earth plus the mass of the Moon times the position of the Moon divided by what? The masses added together. So the mass of the Earth plus the mass of the Moon. Now, what's the x-coordinate for the Earth? 0. So that whole term there is going to go away. And then we can just substitute in. Make sure you convert your kilometers to meters. What'd you get, Maddie? Give me 3 sig figs here. 4.68 times 10 to the 6th, right? Okay. Meters. Is that what other people got? Okay. So we have two answers that are a little bit different. What did anybody else get? Sarah, you're the tiebreaker. Okay. Well, I tell you what, let's just do this. Let's call it 4.7. Okay? Because then that would be what both answers would round to. I used a different value for the distance between the sun and the earth, so my answer is different. But you're in the right ballpark. Okay. And then for part B, what are we supposed to do? So how do I do that? Okay. Certainly don't want that. Okay. So I'm going to take x center of mass divided by the radius of the Earth. So that's going to be 4.7 times 10 to the 6th meters divided by 6.37 times 10 to the 6th meters. And of course, you don't even have to use the 10 to the 6th meters. And what do we get? We'll call it 0.74. So what that's telling us is that the center of mass of that system is inside the Earth. Yes, because it's less than 1 radius. Well, it's the same thing. The Earth is that much bigger. And remember, the center of mass is always going to be shifted towards the larger object. Mm-hmm. Yeah, and the Earth, yeah, although it's a bit more complicated than that, but yes. Okay, we talked about how the center of mass of the solar system would be very close to the center of the sun because the sun is the most massive thing. And it is not only the most massive thing, it is the most massive thing by far. Okay, we don't have time to do the next problem, and I don't want to stop in the middle because we've got a nice 3-day weekend. Please check the portal. Yeah. Please check the portal for a reading assignment for Monday because we've got a long. Although I think by the time we finish up what I assigned for reading for today, we should be okay. And bring on Tuesday the break homework, okay? And we'll go over that. That'll be a good use of our time on the long. See ya.